When mercury has a toxic impact, it's usually in aquatic systems. So you are probably aware of mercury consumption advisories in fish, for example. So even though the place where we worry about mercury pollution is usually in the water, most mercury is actually emitted into the atmosphere, and it will go around the globe, undergo chemical reactions, and what happens in the atmosphere with transport and chemistry really determines where mercury ends up and has a toxic impact, you could say, and rather than where the pollution source is, because it will get into the air and can travel long distances. So understanding how much is in the air, what kind of mercury, kind of its chemical nature in the air, and where chemical reactions and deposition occur helps us understand where mercury that might be, say, in the San Diego Bay came from before it got here. The biggest challenge to measuring atmospheric mercury is that the concentrations in the atmosphere are very low. We measure it in the low parts per quadrillion range, and our research group focuses in particular on oxidized mercury compounds. They exist in the range of about 0 to 10 parts per quadrillion. So that's 0 to 10 molecules of oxidized mercury per quadrillion molecules of everything else. There are two other challenges. One is that oxidized mercury compounds are only a little bit volatile. So they may exist in the gas phase in the atmosphere, but as soon as they come into contact with the surface, they want to stick to it. Any surface really, even like Teflon or something very inert. So that's a challenge, keeping them in the gas phase long enough to analyze them. The other challenge is that they tend to be chemically labile. They'll break apart back to elemental mercury and other stuff very easily. So we have to find surfaces and ways of handling them that are extremely inert and also warm to keep them in the gas phase. There's several really good commercial analyzers for elemental mercury in the atmosphere that can measure those low parts per quadrillion levels well. Elemental mercury is fairly inert and more volatile than oxidized mercury. Our effort has been to develop alternative methods, and we've worked with a lot of partners to do that. One instrument that we've put together measures oxidized mercury indirectly. You measure total mercury, you measure elemental mercury, and then take the difference. And that's challenging because there's a lot more of total mercury and elemental mercury than there is oxidized mercury, so we have to make very precise measurements. We've been able to do that and demonstrate that in a couple of cases. Another aspect of our work is making sure the measurements are correct, so building calibration systems. Something we've been working on for really about 10 years is methods to calibrate oxidized mercury, and we use permeation tube-based methods that are NIST traceable and can deliver these very low concentrations of oxidized mercury in ambient air while these systems are sampling ambient air, because we found that mercury measurement systems can behave differently in ambient air versus like an inert gas or a scrubbed air.